Today I am going to explain you law of Malus. This law is in the field of optics and it is related with a phenomenon called as polarization. It is called as law of Malus because it was discovered by E.L. Malus. Let me explain you the theory behind this law now. Let me explain the difference between unpolarized light and polarized light. Unpolarized light is a light which vibrates in all possible directions. You take any angle, there will be a vibration along that direction. So the light is coming towards you and it has all electric vibrations in all directions. Now if you put a polarizer in the path of this light, then it will allow only those vibrations to pass ahead which are parallel to its optic axis. So after passing through polarization, polarizer, you will have only one vibration or vibration in only one direction, and rest of the vibrations will be eliminated. Now suppose we are using two polarizers in the path of light, and suppose the angle between first polarizer and second polarizer is theta. So now this is the light passed by first polarizer and second polarizer is here, and this light will make an angle of theta with respect to optic axis. Now suppose the intensity of original light is I naught, and suppose the total amplitude of this light, unpolarized light, is E naught. So after polarization, the intensity will reduce because most of the vibrations are eliminated, and you will have an reduced amplitude. Suppose that amplitude is E1. So and then the intensity passing through first polarizer will be I1, and that can be shown that it will be I naught by 2. The reason is that there are vibrations in all directions, and then you can imagine a coordinate system having y-axis along the optic axis and x-axis perpendicular to it. So all these vectors can be resolved along y and x direction, and when you take the sum total of all the components in all the directions, the sum total of y component will be 50% and sum total of x component will be 50%. In another language, when the light is polarized once by using one polarizer, the intensity will reduce by 50%. So we have I1 is equal to I naught by 2. Now we are holding a second polarizer in the path of this light now, and the light is coming from behind. What happens is that the optic axis of second polarizer is here, and then we can resolve E1 into two components. One is E2 is equal to E1 cos theta. This is obvious because this is E1, this is theta. So this component will be E1 cos theta, and a component perpendicular to perpendicular to optic axis will have E1 sin theta. Now let me repeat, the polarizer allows only that light to pass ahead which is parallel to its optic axis. So now E1 sin theta is totally perpendicular to optic axis, so it will not be passed, it will be eliminated, and E2 is equal to E1 cos theta is along the optic axis, so it will be passed. So we are getting a statement where we have E2 is equal to E1 cos theta. What is theta? It is the angle between two polarizers, the angle between their optic axis. What is E1? It is the amplitude of light transmitted by first polarizer. What is E2? It is the amplitude of light passed by second polarizer. Now we know that intensity is proportional to amplitude square. So let us square both the relations. We will have E2 square is equal to E1 square cos square theta. Now since intensity is proportional to amplitude square, I can write down I2 here, and that will be equal to I1. For E1 square I am writing I1, and I will have cos square theta. So this is a statement of law of Malus. I2 is equal to I1 cos square theta. That means when you pass light through two polarizers, the intensity passing through second polarizer will be a cos square function of theta, which is the angle between their optic axis. We can also write down this law in this form: I theta is equal to Im cos square theta. The reason is that I1 is the maximum possible value of I2. Let me explain how. When you put theta is equal to 0 or 180 or 360, then cos square theta will be 1, and then you will have I2 is equal to I1. And for all rest of the thetas, the value of I2 will be less than I1, and it will depend upon theta. So we can also express law of Malus in this form. It has many practical applications, but before that I want to demonstrate this law at first. The apparatus that you require for this experiment is sodium source, which is monochromatic. You can also do this experiment with white light, no problem. and then we have two polarizers. One polarizer, the first one is called as polarizer, and generally the second polarizer is called as analyzer. You can see that the polarizer can be rotated, and if you look from this direction, then you will come to know that there is a pointer, and the angle or angular position of polarizer can be rotated, it can be noted here. So the experiment is very simple. What we will do, we will vary theta and we will measure I theta each time, and then we will calculate I theta by Im, and then we will plot the graph of, we will also calculate cos theta, we will also calculate cos square theta. So when we plot the graph of I theta upon Im versus cos square theta, naturally it will be a straight line. It is according to this relation. This implies that I theta upon Im is equal to cos square theta. That's why it will be a straight line having slope 1. And if you plot the graph of I theta upon Im versus theta itself, then the graph will be like a cos square function. So these are the two graphs which we want to verify in the experiment. So polarizer 1, polarizer 2, that means analyzer, and this is a lux meter which can be used to measure the intensity of light. The sensor of lux meter is here, and it is always better to keep minimum distance between the sensor and the second polarizer. So now we want to begin our experiment with theta is equal to 0. Now question is, what is theta is equal to 0 position? See, it is, theta is the angle between optic axis of two polarizer, and optic axis is not visible. It is not a direction which can be visualized. So how do we come to know that we have got theta is equal to 0? What I want to say is that when you put this pointer on theta is equal to 0, on 0 angle, 0 position, that does not mean then the angle between optic axis of this and this polarizer is 0. So how do we get theta is equal to 0 then? What we do is that we keep a watch on lux meter, and then we rotate the second polarizer through all 360 degrees, and then we keep on monitoring the intensity. At theta is equal to 0, the intensity is going to be maximum, or conversely, when the intensity becomes maximum, that theta angle between these two has to be equal to 0. Now at that time, the position of this pointer may not be 0. Suppose it is 67. So I have got some intensity I theta at theta is equal to 0. I will record it by using lux meter, and then I want to increase theta to 30. So you will have to rotate this polarizer by 30. What I want to say is that when for theta is equal to 0, the pointer position was theta dash is equal to 67. Suppose this is arbitrary, it can be 37 also. So if you want to increase theta from 0 to 30, we will have to move the pointer from 67 to 97. Now if you want to get theta is equal to 60, we will have to move the pointer from 97 to 127. So the difference between the angles will be 30 only, but the values of theta dash and theta, they will be different. So we take the readings at 30, 60, 90, 120, 150, 180, 210, 240, 270, 300, 330 and 360. We are aware about the properties of cos function. Cos 0 is 1, cos 180 is minus 1, and cos 360 is 1. So cos square 0, cos square 180 and cos square 360 will be all 1. So let me come back to the apparatus. Suppose we have recorded a position where intensity is maximum. You can cross verify that by moving the pointer slightly up and down, and then you can record that position, and we know that since intensity is maximum, that position corresponds to theta is equal to 0. Now increase the pointer position by 30, intensity will change now. Record that intensity, then once again go ahead by 30 degree, record the intensity, then again by 30 degree. So in this way you can keep on taking various values of theta like 0, 30, 60, 90 up to 360, and you can record the intensities. Now our mathematical statement is I theta is equal to Im cos square theta. So we know that when theta is 0, I theta has to be equal to Im. So this means that the first value of I theta or the value of I theta at 180 or the value of I theta at 360, they are all Im. So the first value is Im. Now how do we calculate I theta by Im then? We divide every value of I theta by the first intensity which corresponds to Im. So we can calculate I theta by Im in that way. Then we can calculate cos theta and we can calculate cos square theta. I repeat, we are dealing with two angles here. One is theta dash and second is theta. Theta dash is the pointer position of second polarizer and theta is the angle between optic axis of this polarizer. And when theta is 0, we mean that the intensity passed by second polarizer is maximum amongst all the intensities. So after recording all the angles and after doing the calculation, you can plot the graphs. One is I theta upon Im versus cos square theta and second is I theta upon Im versus theta. It will display a cos square function. Now there is one more application of this law which can be verified in the experiment, and that application is that using law of Malus we can prove that laser is a polarized light. So in sodium light, in case of sodium light, we use first polarizer to polarize it, and that polarized light passes through second polarizer, analyzer, and then you can verify law of Malus. Now laser is already a polarized light, so you don't require any polarizer to polarize it. So what I am doing is that I am switching off the sodium source and I am keeping a laser in the path of in the beginning. I am replacing sodium source by laser source. So let us make laser on. You have to adjust the orientation of laser such that it falls totally on the analyzer. That means 100% area of the analyzer should be covered by this laser, and then when it passes through this polarizer, it will fall on the sensor. Take care that this is aligned in such a way that total area or the total laser is covering the total area of the sensor. Now the experiment is same. What you have to do is that you have to rotate this polarizer to different angles. You have to rotate it through all 360 degrees. And you have to stop at a position where intensity becomes maximum. That corresponds to theta is equal to 0 position. And then that angle has to be recorded. Suppose it is 37. And then each time you have to record the intensity at first at theta is equal to 0. Then each time you have to move the pointer by 30 degree. You have to take it ahead by 30 degree and you have to keep on recording the intensity. So experiment is same. But the thing is that in this experiment, we are not using any polarizer to polarize the laser. This is an analyzer which is used to polarize it. When you plot the graph of these two, graphs for laser, you will find that even if there is no polarizer, the laser displays this kind of graphs. I theta upon Im versus cos square theta is straight line, and I theta upon Im versus theta is a cos square function. So this proves that laser is a polarized light. You don't require any polarizer to polarize it. Many experiments are possible. For example, we can replace this laser once again by a polarizer like this, and then we can keep an optically active solution in their path. Optically active solution means sugar solution, for example. It can rotate the plane of vibration of light by theta depending upon concentration. That angle can be determined by using a system of polarizer and analyzer. Law of Malus has many applications. Let me cover the applications of law of Malus. Polarizing sunglasses are based on law of Malus. When you pass a light through polarizer, only vibrations parallel to optic axis are transmitted and rest of the vibrations are eliminated, and therefore you can cut the glare of light by using polarizing sunglasses. Another application of law of Malus is Polaroid cameras. You know that when you fit a Polaroid on the camera, the intensity, the sharpness of the picture becomes better because the glare is reduced. Then one more application of law of Malus is saccharimetry, where we can record the concentration of sugar solution. Then 3D movies are also based on law of Malus. The most important application of law of Malus here is liquid crystal display. It may be a black and white display or it may be a colored display. Both these displays are based on law of Malus, and an experimental technique called as photoelasticity, that is also based on law of Malus. So law of Malus has many practical applications. We can verify this law by plotting the graph. You can see the observation table, theta dash, that means pointer position on second polarizer, then theta 0, 30, 60, where theta is equal to 0 gives maximum intensity. Then all I theta values, then I theta by Im, that means dividing all intensities by first intensity, then cos of theta, not cos of theta dash, calculate cos of theta and calculate cos square theta. Once you get these values, you can go for graphs. I theta upon Im versus cos square theta will be a straight line, and I theta upon Im versus theta will be a cosine square function. So here are some demonstrations of law of Malus. These are polarizing sunglasses. You can see that when the second polarizing sunglass is made perpendicular to first one, the light is extinguished. It is because we have I theta is equal to Im cos square theta, and when theta is 90, cos square theta will be 0, and therefore 0 intensity is passed. Here we are taking the images of light coming through second polarizer. When two polarizers are parallel, theta is 0, maximum light is passed. But when that theta is increased, the intensity keeps on reducing. And here, when the angle between second polarizer and first polarizer becomes 90, the intensity is totally eliminated. So double refraction can also be explained with the help of law of Malus. You are observing that light is passing through a doubly refracting crystal here. So you get two refracted images. One is called as E image and second is called as O image. The vibrations of E and O, they are perpendicular to each other. This means that when you rotate the polarizer, when you see E image, you will not see O image. It is absent here. And when you see O image, you will not see E image. So double refraction can also be verified with the help of this law. And I had told you that liquid crystal displays are based on law of Malus. Colored LCD displays are also based on law of Malus. And this is another demonstration of law of Malus. This is just a mobile phone having LCD screen. We are putting a polarizer over that, and when we rotate the polarizer, it so happens that intensity keeps on reducing, and then finally when you keep polarizer like this, nothing is seen. So this is also law of Malus. Here the optic axis of polarizer is parallel to the light coming from the LCD. Light coming out of LCD is a polarized light, and when you make polarizer perpendicular to that light, the intensity will be eliminated. So this law was discovered by E.L. Malus, who was a French physicist. He himself has coined the term polarization. He also discovered polarization by reflection. His name is one of the 72 names inscribed on the Eiffel Tower.